Une minute. Je vais te présenter, puis après tu pourras commencer, ça te va? Tu es prêt, j'imagine?
Bien sûr.
Okay, on va commencer. So welcome everybody, welcome back. And it's my pleasure to introduce Tristan Ozuch from MIT. And he'll speak about non-collapsed degeneration and desingularization of Einstein four manifolds. Tristan, à toi de jouer.
Thank you very much for the introduction and for the invitation, Grenoble. So yeah, today I'm going to talk about Einstein four manifolds, but in a different way than Antoine yesterday. So he talked about the collapsed situation, and I'm going to talk about the non-collapsed situation where there are still unanswered questions. And so yeah, I'll call there will be some type of degeneration in this setting, and we will see that the opposite is the desingularization. Okay, so let's start. Okay, so an Einstein metric has constant Ricci curvature, so that's already a nice enough equation for that motivates the study of these metrics. But my very favorite way to motivate them in dimension 4 is that they minimize the L2 norm of the curvature whenever they exist on a given manifold. So there is a strong link between Einstein metrics and the topology, the underlying topology. So the L2 norm of the curvature by Cherenkov-Bonnet formula decomposes into two pieces. One is purely topological, it's the Euler characteristic, and the other part is non-negative and vanishes exactly on Einstein metrics. So I like Einstein metrics because they minimize this energy, and there is a very nice topological geometric formula. Okay, so we have a nice equation, the Einstein equation, and we want to understand the set of solutions to the equation. And noticing that the equation is invariant by two trivial actions, by reparametrization and rescaling, we define the moduli space of Einstein metrics, which is the set of Einstein metrics modulo these two actions, modulo rescaling by fixing the volume equal to 1, where Antoine was fixing the sectional curvature between -1 and 1, and also quotienting by the diffeomorphism group, which reparametrizes the manifold. So on this space, the natural distance is the Gromov-Hausdorff distance. And as often when we are studying moduli space, there are natural questions, which are what are the global properties of this moduli space? And here we will see that there are several types of degenerations. And so the question becomes, can we compactify it? And with some structure maybe to understand the Einstein metrics from the global properties of the moduli space. And also the moduli space is a topological quantity. It only depends on the manifold here. So this might give some information about the manifold itself. Okay, so there are degenerations, and you've seen with Antoine that there are collapsing degenerations. So take just in dimension 2, this already appears. Just take a torus and fix the volume equal to 1 and let one of the length go to infinity. Well, you end up with something with infinite diameter, but which is one dimension below. You can also find cusps in a hyperbolic geometry. And again, this appears with infinite diameter, and this already appears in dimension 2. So in dimension 4, the situation is a bit more complicated, but there is also a compactification in the Gromov-Hausdorff sense. So it's been done by several people that you can see here. And this compactification here has 3 pieces. So the first one is just our smooth metrics. So nothing new here. The second part, which is not well understood here, I won't talk about it today, but this is not well understood. This is the limit of collapsing and cusps formation. This is similar to the 2-dimensional situation, but this is not well understood in dimension 4. But today I'm going to focus on this last piece, which is what we call the singular Einstein metrics. And they can be as bad as just Einstein orbifolds. I'm going to tell you what this is right after. And so we will only focus on this piece here, which is the metric completion with the Gromov-Hausdorff metric of the moduli space. So we won't give a structure to the compactification, but only the completion for now. Okay, so what are these singular spaces? They are Einstein orbifolds, and this is not so bad. They are smooth everywhere except at a finite number of points. And these singularities are, again, not so bad because they are just quotient of the Euclidean space, and they just look like, with only one singularity, and they look like the cone on the top left here. In order to construct examples of such metrics, just take some quotients of your symmetric metrics. So take the Poincaré disk, for instance, and an antipodal identification, and you'll find an orbifold singularity here of the type R4 mod Z2 or mod plus minus. And you can do the same on your sphere, just on the cross section, and you'll find what we call the American football metric with 2 singularities. You can also do the same on your flat torus, and you'll find an orbifold with 16 singularities. So in dimension 2, there are only 4 of them. This is your pillowcase metric, but in higher dimension, this is a bit more complicated. So singularities are really not so bad, and the analysis is exactly the same as on the smooth metric. Now, the next step is understanding how these singularities appear. Well, they appear by blowdowns of some bubbles, and the bubbles of the problem here are Ricci-flat ALE metrics. So they are Ricci-flat, and they are asymptotic to one of the cones I mentioned. So the bubbles, the infinity of the bubbles and the singularities coincide, and I mean that's how that's the link between the blowdown and the singularity which forms. And the way these singularities form is really simple. It's just a rescaling, essentially. And the simplest example of this Ricci-flat ALE metric is the Egrush-Jensen metric. It's Ricci-flat and asymptotic to this simplest cone I already mentioned a few times. So how do we create a singularity? Well, just take your metric, multiply it by a small factor t here, and let this factor go to 0. That's just a rescaling. And by definition, by letting t go to 0, just by definition of the asymptotic cone, you converge to the cone. And you created here a singularity. And every singularity really appears that way. So it's not so bad, but that's how they appear. And more generally, you may have singularities appearing on top of each other. So here you have a singularity, a bubble with other bubbles appearing on top of it. You may have several singularities at once, but that's the analysis is always localized, and so it's not a problem for us. And let me mention that maybe the main challenge, the biggest question in all of this study, and also in the study of Ricci flows, as you will see with Richard Bamler, I think it's today, is understanding these Ricci-flat ALE metrics, because they model the singularities, and from them we can understand Einstein metrics and Ricci flows much better. The only known examples are quotient of hyperkähler metrics called gravitational instantons. And a long-standing question is whether or not this is the complete list. Okay, so now I'm gonna just give you a list of questions and answers, just to give a plan for the rest of the talk. And so what we've seen so far is that a bounded limit of Einstein metrics is an Einstein orbifold. And the natural question is the converse, or all Einstein orbifolds limit of Einstein metrics. And if you reword it, it becomes, can we desingularize every single Einstein orbifold? That would be our question here, and that's an old question. And this year I finally answered it. And well, this simplest orbifold I presented to you, this American football metric, cannot be desingularized by smooth Einstein metrics. And that's maybe the newest result I'll present today. And what's maybe striking is that this space is Einstein in a synthetic sense, in neighbors sense, for instance, but it cannot be approximated by smooth Einstein metrics. And so, yeah, the same kind of result in the RCD situation would be amazing. The Einstein equation is quite different, but that's also one way to see to interpret this result. Okay, so we cannot desingularize everything. So the next question is, what can we desingularize? So in the asymptotically hyperbolic setting, what can be desingularized is quite well understood by Picard. And essentially, this becomes much easier because you have a conformal infinity. And I mean, you can send your problems to infinity in some sense. And the problem is purely local. Now, the next step is to understand the same question, but in the compact setting. And let's say, what can we desingularize by just a Gaussian matrix? That's the first question. And I'm going to answer by another question, which is, well, does it impose reduced holonomy? Does the orbifold in the limit have to be Kähler-Einstein in order for the desingularization to have any chance to work? And here, this needs a second order version of Picard's result, and this is very different because the problem is global here. And let me mention that even if we were able to solve this question, this would not be the end of the story, because even in the Kähler-Einstein setting, there are obstructions which are very different in nature, but that we also do not really understand. Okay, so that's the desingularization question, but there is also another thing on which these desingularizations give some information, and that's the structure of the moduli space near its boundary. So just the structure of this completion. So the first one is a convergence result. The convergence is not only just a Gromov-Hausdorff convergence, it's C-infinity in some weighting sense. So it's a very strong convergence that will let us use some techniques from analysis, while Gromov-Hausdorff would not let us understand anything. Another important result, probably the most important here, is that every single Einstein metric, which is Gromov-Hausdorff clause, so again, a clause in a very weak sense, can be produced by a somewhat explicit procedure, which is a gluing-perturbation procedure. So we can reconstruct every single Einstein metric as long as it is a Gromov-Hausdorff clause to an orbifold. And this also gives some structure to the moduli space. It's the zero set of a C1 function on a C1 submanifold of metrics. And this C1 submanifold has its dimension only bounded by a function of the diameter and the Euler characteristic. And maybe you can replace the Euler characteristic by lower bound on the scalar curvature in dimension 4. And that extends, in some sense, the result of Gallo, which also required some bounds on the sectional curvatures. Another question, which I think is really exciting, is to understand the size of this singular set here in order to understand better the topology of the moduli space. And the question of Anderson is whether or not this set of of singular metrics is of codimension 2. And well, I show that this should be true. This is true up to second order if the bubbles are Gaussian. Okay, so that's my list of questions and kind of answers. Somewhat. So just like this one, there are not always complete answers, but that's what we have so far. And let me start by the beginning. How do we go from Gromov-Hausdorff to a smooth convergence? So first, how do we desingularize an Einstein metric? Well, by gluing perturbation. So take a Ricci flat Haley metric, an orbifold, and assume that they have the same asymptotic cone. Take a small parameter and multiply your Ricci flat metric by it. Well, you end up with two metrics which are close to a cone here. And in particular, you can identify some annulus in which the two metrics are really close to each other. And then you can just glue the two metrics together by using a cutoff function on this green region. So this is very a completely dumb way to glue the two metrics. If I asked you to do it in the simplest way, you would have done exactly the same thing. So it's a very naive way, and I even call these desingularizations naive. And I'll denote them GDT for desingularization. And now we have our gluing. The question now is, can we perturb it to an Einstein metric? And this is always the much harder step. And understanding the perturbation means understanding in which function space we want to do that. So usually in gluing perturbation, people create function spaces in order to be able to do this perturbation. Here we have a different goal. Our goal is to find how close our Einstein metrics are and to use function spaces which are modeled on this closeness. So we have a different problem. And so our which function space question is not in which function space will we be able to do the perturbation. It is in which function space do we actually have closeness. And this has been answered by this first theorem. So take an orbifold and now take an Einstein metric which is close to the orbifold in a Gromov-Hausdorff sense. So that's the weakest assumption you can make. Then there exists a naive desingularization, mGDT, so that the Einstein metric is not only Gromov-Hausdorff close, but it's close in some weighted Holder sense, in a very strong sense here. So our naive desingularizations are not so naive. They are actually good approximations of actual Einstein metrics. So what are these weighted norms? Well, they look like this. So when you have, so here you have a natural norm on cones, but here you have a weight, and that's this G of R. And understanding the norm means understanding this weight. And well, being bounded for this weighted norm means being less than the function, at least in a C0 sense. And so what is this function? Well, it looks like this. It's just one on your large compact of the orbifold and of the bubbles. But in the neck regions, which link the bubble and the orbifold, so in this neck region, you actually have a decay here, a polynomial decay even. So you are not asking for a convergence speed on these large parts, but you are asking for a convergence speed in the neck region. That's very different from the usual norms coming from gluing perturbation, where the typical norm is like this one above, used by Picard, for instance. And what's very different is that it asks for a convergence speed on the orbifold part, and it's usually not satisfied. I mean, it's almost never satisfied. And so we gain something by just not asking this. And so something which is even more important for us is that this new norm handles several singularities, but also trees of singularities. You can handle singularities appearing on top of each other by just asking decay on each neck region. And so the way we prove it, so on the white regions here, the metrics are just Einstein metrics with bounded, with harmonic radius bounded below. And so by just epsilon regularity, the two metrics are close to each other. So my Einstein metric here is always close to its blowups. So it's close to the orbifold metric. On the white region here, it's close to all of these bubbles rescaled on the other white regions. So the white regions are fine. We are done on these regions. And so the whole difficulty is really these neck regions. How do we deal with these AK, AJ, AL? And how do we relate them to the green regions here? And in darker green is the gluing region in where the metrics were cut off to each other. And so you see that there are several parameters in the gluing, and they look like this. So the way these neck regions are bad because you have arbitrarily different smaller and larger radii in these regions. And so all of these epsilon regularity theorems give you nothing. They just give an error that blows up. And so my idea was to use to construct some new coordinates in these regions by some CMC foliation. And what's great about them is that their intrinsic and extrinsic geometry is purely controlled by the ambient curvature. So you obtain really optimal control of them. And so this ambient curvature was controlled by Bando, where he had exactly the type of control I needed. And this makes me construct optimal coordinates whose spheres are these CMC hypersurfaces, so constant mean curvature hypersurfaces, and they are optimal by just the fact that the intrinsic and extrinsic geometry here is controlled by the ambient curvature. And in particular, we get a control like this for the metric, which was the expected control. So that's roughly the steps in order to find a better convergence. So every Einstein metric which is close to an orbifold is a perturbation of a naive gluing. Let's now look at the converse. Let's take a naive gluing and let's try to perturb it to an Einstein metric. And that's the next theorem. That's a partial converse. So let's take a naive gluing with a small enough parameter. That's what we want to approximate. We want to approximate something which is close to an orbifold. I think there is a question. What do I mean by optimal coordinate? I mean that the control of the metric in the coordinates is as good as it gets. So the metric is as close as a Euclidean metric as the curvature is small. So you cannot expect your metric to be closer than that because the curvature is there. That's what I mean. Thank you. Okay, so now let's take any naive gluing with small enough parameter. Well, we cannot perturb it to an Einstein metric, and that's the whole point. Often we cannot perturb it to an Einstein metric, but what we can always do is perturb it to an Einstein modulo obstruction metric. So this is not solving the Einstein equation, which would be just this equal to 0. We solve it up to some explicit set, which I call the obstructions, and which you want to think of as the co-kernel of the linearization of the Einstein equation. So that's quite typical. You cannot always, if you have some, if you are not surjective, then you cannot solve your equation, and that's exactly what's happening here. So at this point, we are not really happy. We have not constructed Einstein metrics, and yeah, no one should care about these metrics. They are not geometrically motivated or anything like this. They are just, yeah, they just come from an analysis problem, and at this point, we do not really care about them, but what makes them interesting is that they reach every single Einstein desingularization. So we have constructed every single Einstein metric. The question now is, when does this equal 0? And when it does, we have exactly an Einstein metric. And so we have reconstructed a whole neighborhood in a Gromov-Hausdorff sense of the moduli space, close to one of these orbifolds. So that's why these metrics G hat T are useful. They are just, whenever the obstructions vanish, they are Einstein metrics. And you see here that my C1 function, of which the moduli space is 0, is this O hat T. That's my C1 function. And the G hat are my submanifold in which we want to find the zeros, which are exactly the moduli space. Okay. So now, yeah, sorry. Let me come back here for 1 second. So that equation here is my obstruction. Whenever it cannot be satisfied, then you cannot find any Einstein metric here. So when the equation O hat not is equal to 0 cannot be satisfied, you cannot find any Einstein metric. And that's my obstruction result. And first application is that if you take a sequence of Einstein metrics converging to an orbifold, but with a given topology, which is the topology of the desingularization by gravitational instantons or their quotients, then you find an obstruction, which is that the kernel of your self-dual part of the curvature is at least one-dimensional. So you need to have a 0 in your curvature for the gluing to make any sense. So this is an actual obstruction because this is not satisfied by S4 mod Z2 or H4 mod Z2. And let me note that this was already identified by Picard under technical assumptions on the orbifold that I will mention later, and assuming that there are Eguchian metrics and and more and something which was more disappointing, which is that he had to assume a convergence in weighted Holder spaces. But this convergence is usually not satisfied. So that was the reason for my whole PhD, which I did under his supervision. He wanted me to go from this weighted Holder space to, I mean, from Gromov-Hausdorff to some nice space. And that was our first theorem. And so here we get a general obstruction result in which you can have deformations for your orbifold as many singularities as you want and trees of singularities forming. The obstruction will still hold. So some example of application. So you may want to try to desingularize this American football metric by gluing two Eguchian metrics at the two singularities. But the theorem tells you that it's impossible. You cannot perturb it to an Einstein metric. What you can do is perturb it to something which has pinched Ricci curvature in an LP sense and maybe some bound on the Ricci curvature if you want. And that's fine, you can do it, but you cannot have the exact equality. And an open question for people interested could be to try to do the same thing with L infinity instead of LP. And I don't know what should be the answer. So this was an obstruction under some topological assumption. Another assumption that you can make is that you are spin. And again, for your right singularities, you will find the obstruction. But here, this year, I have a new result, which is that the obstruction is general and does not require any topological assumption for a spherical and hyperbolic orbifold with singularities like this. So for instance, your American football metric cannot be limit of smooth Einstein metrics. It's impossible to approach it in a Gromov-Hausdorff sense by smooth Einstein metrics. And so I want to spend some time just giving you some ideas which motivated this, which are parts of the proof of it, but maybe not direct parts of it, but which I think are useful in other settings. So let me just give you some formulas and results. Okay, so it starts with the question of integrability of Einstein deformations. So take an Einstein metric. So we say that an infinitesimal Einstein deformation is just a deformation so that the Einstein equation is satisfied at a linear level. That's just a linearization of the equation. And we say that this deformation is integrable when it's the actual first derivative of a curve of Einstein matrix. So integrability implies clearly the infinitesimal, the fact that you're in infinitesimal deformation, but the opposite is not always true, and that's a very delicate question. So, okay, so one of the main tools, I think it's very simple but very useful. At least it was useful for me. Is that you? I will relate it to this question of integrability right after. But we have nice formulas by integration by parts, essentially just your divergence theorem. So just take T, divergence free. And divergence free is our assumption here, and that's always what's important in all of these proofs. Then you have two formulas, two just integration by parts formulas. And the second one is really similar to Schoen-Spohodzeif identity for a scalar curvature. So for Schoen-Spohodzeif identity, just replace T by Ricci minus the scalar curvature over 2 times the metric. That's divergence free. And you find Schoen's formula here. And what's important here is that if X is killing, then here you have just 0. And if here the trace is constant, and if you have a conformal killing vector field, then here you also have a 0 right-hand side. Conformal killing. And here the trace of T is constant. So for instance, if we take this example of a Schoen, T, the trace of T, is a multiple of the scalar curvature. And an Einstein metric has constant scalar curvature. So this should vanish, and this will vanish if you take a conformal killing vector field. So these are very simple formulas, but they are very deep, and they have some information, and this term will be important for us as well. So what's the link with integrability? So let me take E of G to be the tensor I mentioned, which is divergence free. And a very simple result is that if G is Einstein, then any linearization of this tensor is divergence free. So you can directly use your divergence theorem to this tensor, the linearization in the direction H. And if you have a killing vector field which kills the right-hand side, you will find this identity for any hypersurface and any killing vector field and any symmetric two tensor H, you have this vanishing, you have the vanishing of this quantity. And the idea is quite simple. Take sigma here, perturb it a little to sigma prime, and take a cutoff function, say, which is like this. So say that this is 1 in the neighborhood of sigma and 0 after sigma prime, and multiply H by this factor. Then in the previous formula, this boundary term is only seeing the sigma part, because that's where there is some mass because of the cutoff. And so this integral here is just equal to the whole boundary term, which is 0 because we have a killing vector field. So the right-hand side in the previous formula, let me just show it again, here vanishes. So you have just this thing equal to 0. That's a very simple proof, but that's a deep result. Let me mention that was done in the Lorentzian setting, and I'm extending it to the Riemannian setting with exactly the same proof, and I will give you some other extension of this. Okay, so here so far there is no link with integrability of infinitesimal deformation. So what's the link? Well, it's here. If you assume that you have an infinitesimal deformation, then the second derivative is divergence free. And so you define what's called Taub's preserved quantity in Lorentzian geometry, and that's this same integral but with the second derivative here. So it's invariant, it has a lot of good properties. And what's great and what's a deep result is that if H is integrable, and say Ricci flat, we won't need that in the Riemannian setting, but that's what they proved, then you have this vanishing. And this vanishing is not always satisfied. There are obstructions to integrability, and there are exactly these ones. So there is a beautiful result by Fischer, Marsden, Moncrief, and you should add Judith Arms as well in this list of names. And these are the only obstructions to integrability of Lorentzian Ricci flat metrics. So if you have a Lorentzian Ricci flat metric, and if you take an infinitesimal deformation which satisfies this equality, then there is an actual curve of Einstein metrics. That's an amazing result. But it uses a lot of this hyperbolic nature of the Einstein equation in Lorentzian settings. So we cannot do it in the Riemannian setting so easily. And the idea, in order to prove this, is again very simple. Just take your metric up to order 3 and differentiate the equation E of G of t is 0. And you end up with this thing here. And if you just integrate this over sigma and apply it to y and your normal, then you find this identity here, and this right-hand side is 0 by the first theorem, the first proposition. Oh, sorry, that's not the h here. That should be k. Sorry, that's k here. That's your k that you find here. So we have a nice abstraction to integrability. So let me. So I wanted to extend it to the integrability of deformations of Ricci flat cones. So let's take a Ricci flat cone, looks like this, and it is Ricci flat. Well, there are very similar obstructions, but this time they are on the Ricci, the traceless part of the Ricci curvature. And they hold for both your conformal Killing vector field RDR and any Killing vector field of GS. Let me see. Yes, here. So yeah, you have these very similar obstructions in the other setting that was E here, but if you want to allow Einstein deformation and not only Ricci flat deformations, then you need some assumptions, and then you can use the traceless part of the Ricci curvature instead of the Einstein tensor. So we have obstructions to integrability of deformations of Ricci flat cones. And what's important for us is that they are equal to many obstructions that we have to the desingularization of Einstein metrics. So take a sequence of Einstein metric converging to an orbifold. And let's assume that a rescaling of it converges to a given Ricci flat Ailey metric. So that's our general situation, but let's use these notations. And let's assume that our two metrics have some expansion. So the first term is the same on both sides, but then there is a H2 and H4, which is the next term in the expansion. So here, this is an expansion at the singular point, and here at infinity. Then there are obstructions to the desingularizations, which look exactly like our obstructions to the integrability. And these are obstructions to the integrability of H4 plus H2, if you think of it, because this is a quadratic form here. And these two were already integrable because just of the existence of GB and G naught. So we can rewrite many obstructions to the desingularization as such an integral. And that's quite satisfying to see the second derivative of Ricci as an obstruction. And that way you recover every obstruction to the desingularization by Eguchianson metrics, for instance. Okay, so that's one new way which is useful to find obstructions. So let me give a few ideas of how from this you can prove that S4 mod Z2 cannot be desingularized. So let's take a non-flat. Not-flat is important here, Ricci flat Ailey metric. But if you take a blow-up, it will not be flat if you take the right blow-up. So the first tool, and which is very important for us, is Bicard-Hein renormalized volume. So whenever you have a Ricci flat Ailey metric, you can define a renormalized volume. It is negative, and I mean it's non-positive and zero exactly on flat cones. And if you take a non-flat Ricci flat Ailey orbifold, then it will be negative. Thanks to the previous formula, you can rewrite the obstruction as okay, so let's take a metric, an orbifold which has lambda as a Ricci curvature and which has zero veil curvature, just like the sphere, just like your hyperbolic metric. Then the first obstruction against one of the deformations of the Ricci flat Ailey cone is lambda times this volume. And so if this is not zero, then and if the volume is also not zero, I mean, it is never zero, sorry, then there is an obstruction. And that means that there is an obstruction to this gluing perturbation. But there is one additional difficulty that that is hidden here, which is the fact that the Ricci-Flat-Haley metric might have non-integrable deformations. So these obstructions to the integrability could compensate these obstruction to the desingularization. These are very different in nature, I mean, in what causes them, but they can compensate each other. And that was the main problem remaining. And so we want now to understand these obstructions to the integrability of Ricci-Flat-Haley deformations. And I want to motivate the fact that, I mean, what we want to prove is that these obstructions cannot compensate the previous obstructions. And let me just mention quickly a few steps of this proof. The first one is that you can take any conformal King vector field of your asymptotic cone, and you can extend them to harmonic vector fields. Then the traceless part of the Lie derivative of the metric in this direction is traceless, divergence-free, and of course an infinitesimal Einstein deformation. But it's not a trivial infinitesimal deformation. It doesn't come from diffeomorphism or something. It's an actual deformation. And if you go a bit further, then the obstructions to integrability are of the form an integral of t against the traceless part of this Lie derivative. And t is divergence-free. According to Shane's Podolph formula, I mean, it's maybe slight generalization. This is equal to, to some limit when r goes to infinity of some boundary term on the sphere SR. And this boundary term is zero just because things decay fast enough at infinity. And so you prove that these obstructions vanish or are small enough so that they cannot compensate the previous obstruction. And so we've used these integration by parts techniques a few times, and they're very useful in this setting. I think that Alex Dorial and Felix Schulz are using similar techniques in the case of gradients expanding solitons. And I think that these formulas can be useful in many different settings. So I wanted to spend some time on them. Okay, so that's our we cannot desingularize everything step. Let's now go a bit further and try to understand what we can desingularize. So we are going to the higher order obstructions, and namely second order obstructions here. So we're going to take the same assumptions as BK, but only assume a Gromov-Hausdorff convergence because we can now. So let's take a compact orbifold. Compact is very important for us. Rigid, just like in Bicard's situation, and assume that there is only one singularity of the simplest type. Now, let's also assume that we have an orbifold which is limit of Einstein matrix on the topology of M naught desingularized by an Egu-Henson metric. That's the topology of an Egu-Henson metric here. Then there is an additional obstruction. So the first obstruction was that this dimension is at least 1. Well, here we prove that it's at least 2. So it's, okay, that's better, that's a stronger obstruction. But what's maybe the most important here is that this is exactly the type of curvature you find in the Kähler-Einstein setting. So this type of curvature is typical of Kähler-Einstein metrics. So our question, so that's since the curvature can be seen as a infinitesimal version of the holonomy, you can say that at some first order you are actually like a Kähler-Einstein metric. There are stronger results in the Ricci-flat setting and even more in the stable Ricci-flat setting, semi-stable for some people. So I say that a metric is semi-stable or stable if the linearization has only a non-negative spectrum on traceless transverse tensors. That means that if you run the Ricci flow, then it will flow back to your metric, for instance. But I allow Ricci flat deformations by non-negative spectrum. There can be zeros here. So let me take again a Ricci flat compact manifold desingularized by a bunch of Augustian metrics. Here you can have many of them. And let's assume that there is a sequence of stable Ricci flat metrics converging to it. Then we have the same obstruction. The self-dual part of the curvature is just vanishing at the singular point. It's important to note that it's only at the singular point at this step that this is true. Okay, so that's a higher order obstruction. Let me mention that it's not true in the non-compact setting. In the asymptotically hyperbolic setting, this is not true. There is a counterexample constructed by Page and Pope. The idea is to take, just this family called ADS top boat. It satisfies all of our assumptions, but the curvature only has a one-dimensional kernel here, so it's not satisfying our second order obstruction. And so the interpretation is that this second order obstruction really uses the compact nature of our metrics, and we cannot send our problems to infinity like you can in the asymptotically hyperbolic setting. So this shows that this second order obstruction is not local, it's a global question. Okay, so now this opens more questions than it answers, but let's mention two of these questions. So let's take a Ricci flat orbifold and desingularize it by Augustian metrics. And the first two obstructions, at least when it's stable, mean that you have an anti-self-dual curvature at the singular points. But you also have an infinite list of obstructions which are on the higher derivatives of your curvature. And my question is, well, does it impose that this self-dual part of the curvature vanishes exactly? And if so, that would show that your limit have to be locally hyperkähler. That would be the very long-term question. Maybe I don't want to call it a conjecture as this step, but if you have a limit of Ricci flat metrics bubbling out Augustian metrics, does it have to be hyperkähler? That would be the question here. And this is true up to second order by the previous theorem. Another theorem, another question, that we partially answer is this question of Anderson saying that the singular set is of codimension 2. So first, this is false in the asymptotically hyperbolic setting with the same counterexample. And this can be rewritten as there exists, just the same conjecture with other words, that there exist desingularizations which are transverse or orthogonal to the boundary of the moduli space. And what I showed is that this second order obstruction is a second order version of Anderson's conjecture. And moreover, every element of this kernel here coincides with an Einstein desingularization up to second order. Okay, so let's now test these higher order obstructions in some example, which is T4 mod Z2, which is of interest. So let's take T4 mod Z2 that I defined before, and let's glue Augustian metrics to it. So we want to glue rescaled Augustian metrics, but we also want to rotate them before gluing. So we apply some element of O4 before gluing. And so if the gluing is done in the positive orientation, then the obstructions are on R plus, and if not, they are on R minus. So the orientation is important for us. Okay, so why is it an important example? Well, it's because Page and Gibbons-Pope gave a picture of what should be a hyperkähler metric on K3 by taking this orbifold and desingularize it by by 16 Egussian metrics, but in the same orientation. They are all in SO4 here. So if you do that, well, it's been proven by mathematicians that you can perturb the naive gluing to a Ricci flat and even hyperkähler metric here. Okay, so we created a hyperkähler metric on a Ricci, but a very important question in geometry is whether or not there are compact, maybe stable Ricci flat metrics which are not hyperkähler or locally hyperkähler. That's one of the biggest questions in differential geometry. Are there compact Ricci flats for manifolds with generic holonomy? So Page has a candidate for that. It's probably the best candidate at the moment, which is to take the same orbifold, but this time glue Egussian metrics in different orientations. And the question is, well, can we perturb it? And if so, this would yield a stable or not Ricci flat metric with generic holonomy. So that's a gluing perturbation problem that people are very interested in, because that would answer this question. So let me talk about this desingularization. So first you have to decide where you put positive and negative orientation of your gluings. There are a lot of possibilities, but then you also still have 57 degrees of freedom. So it's a 57 dimensional space, and 9 of them come from the flat torus, and the rest come from 3 times 16 deformations of the Egussian matrix. My result is that, so we had 57 degrees of freedom. Well, we also have 57 polynomial equations to satisfy. So yeah, in general, just to have a Ricci flat desingularization, you need 57. You have 57 obstructions to satisfy. And if you add the term stable, then it's 84 obstructions. So there are many more obstructions than there are degrees of freedom. And this indicates that, I mean, almost all flat metrics should not be desingularized, at least when you choose the right positive and negative orientations. And the idea is just to consider the partial hyperkähler desingularization and try to perturb this partial desingularization to a total desingularization. And there are obstructions to doing so. And when they are not satisfied, then you cannot do the desingularization. That's where all of these obstructions come from. Maybe more another type of, a true type of obstruction under only topological assumption is that you cannot desingularize the regular torus coming from the usual Z4 lattice by 1 Egussian metric and in one orientation and 15 in the other. If you add the word stable, it's even worse. You cannot do it with at most 3 and at least the rest of negatively oriented Egussian metrics. So yeah, so this was already studied by Brendler and Capouleas, where they use this regular torus, a chessboard pattern for the positive and negative orientations. And what's important is that they have only a one parameter family, because there is only one parameter here, T, which is the scale of all of the Egussian metrics. And they proved that there is one obstruction, and it was used to construct a very, very important and very new type of Ricci flow, an ancient solution of the Ricci flow, which desingularizes the orbifold. That's a striking construction. And this comes from our obstructions. And let me note that in this configuration, none of the 57 obstructions is satisfied. So okay, at this point, you would think that nothing can be desingularized. But I found a family, 14-dimensional one, it's probably much larger, of desingularization of this regular torus, which, because of its symmetries, can be I don't know if it can be desingularized by Ricci flat Cayley metric, but it can be desingularized while satisfying the 84 obstructions. And so the question would be, well, can we desingularize it by actual Ricci flat metrics? And I think this should not be true. I think even higher order obstructions should prevent this, but this is very hard to check. And so that's my last slide of results. And let me just conclude by quickly recalling what we did today. So I'm going to do it chronologically. So in my first papers of PhD thesis, I proved that first the Gromov-Hausdorff neighborhood of the set of singular metrics is described in a smooth sense and not only in a Gromov-Hausdorff sense. And then this let me extend this obstruction that Bicard found to the conjecturally general situation. So most important part is that we only had to assume a Gromov-Hausdorff convergence, but we also could handle any type of orbifold, any gravitational instanton instead of just Eguchi-Jensen, and we could allow several singularities and trees of singularities. So this is the cornerstone of the rest. It's probably the most important result in the list. Then last year in December, I proved these results of higher order obstructions. And this motivates questions rather than it answers completely some questions. The first one is, well, do we have this second order obstruction for any Einstein metric desingularized by gravitational instantons? So I proved it under technical assumptions with Eguchi-Jensen. With other gravitational instantons, it's not so different, but there is some difference. That's the first question, probably doable. The second one is much further away. It's understanding. It's a long-term question, and that's, well, if your bubbles are gravitational instantons, well, is your limit Kähler-Einstein? That's the long-term question. And there is this question of Anderson, which is whether or not the boundary should be thought of as a boundary or actually a filling of missing pieces. So is it a codimension 2 subset or not? And the last one is this question of desingularizing T4 mod Z2 by Ricci flat but not hyperkähler metrics. So that's the results from last year. And this year, I used the analogy between desingularization and integrability of deformations. And this let us recover many obstructions from conformal killing vector field of the cone. So in your neck regions, what's happening is that your Einstein metrics, which are desingularizing an orbifold, are really perturbation of a flat cone. They look like, the neck regions at very small scale really looks like a flat cone. And so our Einstein metric is a perturbation of that, and there is a deformation of it. And the question is whether or not this is integrable. And so there is a link between integrability of these deformations and obstructions to desingularization. And that's what we used here, looking at conformal killing vector fields of the cone. And the main application was the fact that you cannot desingularize spherical and hyperbolic orbifolds with R4 mod Z2 singularities. So thank you for your attention.
Thank you very much, Tristan, for this very precise account of results. So are there any questions? Yeah, Felix is so there are questions in the chat and Felix online. So Felix, please start and then we'll answer the question in the chat.
Okay.
So yeah, very nice, great results. You mentioned this result of Brendle and Capuleas.
Yeah.
So how does this fit in with your obstructions? You said this was completely obstructed, that problem, but they still found the Ricci flow. Can you explain a bit sort of how this connects?
Sure. Yeah, let me come back to it. Yeah, so how do we find a Ricci flow is a bit complicated here, but let me try to say something. So the obstructions when you are gluing, so so the obstructions are really elements of the kernel of the linearization of Einstein for Eguchi-Hansen. And what's important to note is that they look like, there is this O1 obstruction, which is in the kernel of the linearization of the Eguchi-Hansen metric here. And O1 is really equal to this traceless part of the Lie derivative of, here you have your Eguchi-Hansen metric, and that's exactly how you want to write your obstruction. Mm-hmm. And here X is close to RDR at infinity.
So can I understand this? So this is in some sense, you see the force which is opening up the Eguchi-Hansen metric as the obstruction?
Exactly. So solving the equation modulo obstruction gives you that the Ricci of your say your Einstein metric, maybe here it should not be Einstein, but that your Ricci flow is equal to some lambda of t, some constant depending on time, times this O1. And if you look closely, this looks like, I mean, this is a multiple of the metric plus some Hessian of a function. So that's, at first order, your metric is really like a soliton. So it's really, and you see your Eguchi-Hansen, the perturbation of your Eguchi-Hansen metric is not Ricci flat, it's not Einstein, but it's close to being a soliton instead.
Is it clear which soliton you see?
Yeah, because O1 here, this is lambda times t times, I don't remember the numbers, but I think this is 2 times GEH plus the Hessian of some function.
Okay.
With respect to GH. So that's here, it's not the true Ricci curvature, that would be the linearization of the Ricci curvature at the Eguchi-Hansen metric for GT minus GEH. But at the first order, you really see a soliton.
This means if you take the flow and you do a blow up forward in time, you see an expanding soliton at each of these. I guess not really.
Yeah, not really, because
it takes infinite time.
Yeah, exactly. So if you blow up, you will just see the Eguchi-Hansen metric. But at the next order, you see something which behaves like a soliton.
Oh, I see. Okay. And maybe one little technical question. When you look at these Einstein orbifolds which you get, and you desingularize them, do you also get Einstein orbifolds where you converge to the cone at the orbifold point slowly? Or do you always have a polynomial decay rate?
Do you mean with a Ricci flow or?
No, just static. Yeah, when you. I just was wondering if do you have this case that you have Einstein orbifolds where you have more or less non-integrable tangent cones at the orbifold points, or are they always integrables, or do you always get a good decay rate to the cone?
I mean, yeah, no, the cone is always quite. I mean, you really have an expansion of your metric as the cone plus something.
Okay,
which is
so you don't get like in, you don't get like if you have singular like singularities in minimal surfaces where you have like flow convergence to the tangent. You don't have this, so you have always put. Okay, I see.
The cone is
I was just wondering because you had this decay rates, and I was wondering if you have to deal with these much worse decay rates where you. Yeah. Okay. Cool. Great. Thank you so much.
More questions? Okay, so there's nothing in the case that people have questions to ask. So thank you again, Tristan, for this beautiful lecture. Merci beaucoup et bon voyage. Ah, there is a question in the chat. Sorry, it was no, there's no question. Thank you very much. This is a question. Thank you very much. Thanks a lot for this lecture, and see you soon, Tristan.
Okay, bye.
So we'll resume at 4 p.m. Paris time.